Welcome everyone to my talk titled Are Dynamic Memory Managers on GPUs Slow? A Survey and Benchmarks. My name is Martin Winter and I'm a PhD student at the Graz University of Technology in Austria. One of the main challenges presented to the user when trying to port existing CPU algorithms to the GPU is the prevalence of dynamic memory in many algorithms. Contrasting the GPU with the CPU, we find ourselves with orders of magnitude more threads, making locking quite costly, and also different cache architecture. Typical CPU memory managers are designed around one memory arena per core to improve cache hit rates and rely on mutual exclusion for exclusive access to resources. Considering the number of threads and the different cache, which is especially challenging for locking algorithms, we can see that a different take might be required. There are many current research topics on GPUs which would benefit from dynamic memory management, including dynamic graphs, sparse linear algebra operations, or databases. A straightforward Google search or reading implementation guidelines will typically lead to the conclusion to avoid dynamic memory managers, and instead either overallocate or pre-compute the requirements. But neither is always an option, and further cementing the need for dynamic memory management also on GPUs. The first approach was introduced now over 10 years ago, and most research was done up until 2014. The introduction of the Nvidia voltage generation renewed interest, as it brings with it independent thread scheduling as well as scheduling guarantees, allowing for blocking algorithms on GPUs. The next slide will present a condensed timeline. For each approach, I'll note the conference and year it was published at, as well if it's publicly available and if it natively builds on the new architectures. Nvidia introduced their allocate interface already in 2010, in the same year that X-Malloc by Huang and colleagues was introduced. This was followed by scatter-alloc in 2012 by Steinberger and colleagues, and FTG Malloc in 2013 by Widmer and colleagues. 2014 saw 3 releases: HALOCK by Adinets and Pleiter, Winkler and colleagues with register-efficient memory allocator on GPUs and 4 variants of their allocator, and Spleet and colleagues with KMA, an allocator for OpenCL. In 2017, Nvidia introduced independent thread scheduling with the voltage generation of cards, sparking renewed interest, which led to 2 publications in 2019. The bulk semaphore by Gelado and Garland with 2 allocators, as well as Dinosaur by Springer and Masuhara. And we contributed the most recent publication, which is called Oroboros and has 6 variants. FTG Malloc and Dinosaur are not strictly general-purpose allocators and have been omitted, while we could not get KMA to build and the bulk allocator is not publicly available, leaving us with 6 approaches and 14 variants in total to test. Before introducing all of the approaches, first let's flesh out some commonalities. All start by pre-allocating a large region of memory, and most do not allow the relocation of this region. This region is then split into chunks, which are further split to serve allocations, some split evenly, others arbitrarily. The allocation status is typically tracked either via lists, queues, or bitmaps. Nvidia first introduced a dynamic memory manager for the Fermi generation of cards, so that's Compute Capability 2.0, with a standard Malloc and free interface, and recently even an option for aligned allocation. Unfortunately, very little is known about the internal structure, and I can only offer some speculation based on our results. It seems that allocations are aligned to a power of 2, which are split from larger chunks. There are multiple chunk sizes, and the first seems to be at around 2 kilobytes, and it seemingly does not benefit from reuse. Overall, reliability is valued over performance. X-Malloc is the first non-proprietary dynamic memory manager on GPUs, introduced in 2010 by Huang and colleagues. Large allocations, as well as so-called superblocks, are served from a heap, which is segmented into free and allocated memory blocks. These blocks are linked together into a linked list, which also allows for merging of neighboring blocks. Such allocations are unfortunately quite slow, as one has to traverse the list to locate appropriate blocks. Therefore, X-Malloc introduces small buffers implemented as FIFO arrays to serve allocations directly. Small allocations, also called basic blocks, are served from one of the first level buffers. Superblocks are split into 32 basic blocks, and the bit mask is used to keep track of the allocation state. Superblocks themselves are also referenced via a second level buffer. Only if this is empty, one has to traverse the initial list and insert new superblocks into this buffer. SCAT-HALOCK was introduced in 2012 by Steinberger and colleagues to address the problem of collisions during allocations. The heap is once again split into superblocks, which are linked together into a single linked list. Each superblock is split into a fixed number of pages, whereas free memory on a page is tracked via page usage tables. Each page is split into equally sized chunks, which are served to the user. Once a page is completely free, it can be repurposed for a different chunk size. For large allocations, such as pages just holding data, but to allow for smaller chunk sizes, which could not be expressed by the bit field in the page usage table, an additional hierarchy of bits can be placed at the beginning of a page. Allocation requests are scattered across its memory regions to reduce collisions during allocation. And furthermore, it tries to reduce the number of data accesses, atomic operations, and also returns data words close to each other for allocations within the same block. In 2013, Widmer and colleagues introduced FTG Malloc, a warp-level optimized allocator designed for small, frequent allocations with the goal to reduce warp divergence. Allocations are always shared by all threads within a warp, and there is no general free mechanic. One can only release all memory on a warp basis. Allocations are organized in a so-called warp header, which keeps track of the allocation state. Small allocations are handled by reserving memory on superblocks. Their most recent is kept extra, while the rest are stored in fixed size lists. As these lists are fixed size, multiple lists might be instantiated. Large allocations are forwarded to the CUDA allocator. HALOCK was presented at GTC 2014 by Adinets and Pleiter. Its heap consists of 2 to 8 megabyte slabs, which at runtime can be assigned to a different allocation size. The global state tracks the number of allocations as well as the currently used slab for each allocation size with a head pointer. Depending on the current fill level, a slab can be either free, sparse, roomy, or busy. Each slab holds a bitmap for tracking the allocation status. While a slab is considered sparse, it can also hold different block sizes. Once a slab reaches status busy, which is after a fill level of 85%, it is replaced as head. The user receives a block, which can be any multiple of the chunk size. The bitmap heap is traversed using a hash function, which is fast and scalable as long as less than 85% of the blocks per slab are allocated. And lastly, allocation state modifications are performed using warp aggregated atomics for increased performance. Winkler and colleagues introduced a paper titled Register Efficient Memory Allocator for GPUs in 2014, which is based on a circular memory pool and will henceforth be referred to as RIFF. The pool is pre-split into chunks with header information, forming a structure similar to a binary heap. Chunks are linked as a single linked list. There exists one global offset, which is altered using atomics. An allocation might split a chunk if it is large enough, or simply take the next chunk in line. Deallocation only sets the corresponding header information per chunk, but neighboring free chunks can be merged again. 3 additional variants were proposed. One fuses the header data for more efficient atomic access, another introduced one offset per multiprocessor, while the last combines both approaches into one. In the same year, Split and colleagues introduced KMA, a 2-layer memory manager for OpenCL, with a lower-level access interface with direct malloc and free access, and a higher-level allocator for larger structures. Its heap is split into superblocks, which are split into power of 2 aligned pages. Superblocks are located using a hash map. If none are available, one is taken from a free list implemented as a lock-free queue. The superblock state is then used to locate the page to return to the user by iterating over its bitmaps. Dinosaur is one of the recent additions by Springer and Masuhara in 2019 and intended to solve the problem inherent in object-oriented programming, as you typically have structures which are stored in arrays, leading to suboptimal memory access performance on GPUs. They propose a memory allocator as well as a DSL-like data layout and a do-all operation on these structures. With Dinosaur, one can allocate predefined structures, and internally, objects are then stored in a structure of arrays approach for improved memory access performance on GPUs. Also in 2019, Gelato and Garland presented a paper, Throughput-Oriented GPU Memory Allocation, which introduced a new synchronization primitive for GPUs called the bulk semaphore, which allows for preemptive batch allocation. Furthermore, they introduced two allocators, a tree-body allocator for large allocations with one bulk semaphore per level in the tree, as well as the unaligned allocator for smaller allocations, modeled after CPU allocators. It has one arena per multiprocessor, as well as per-size bin lists secured by a bulk semaphore, which has also a list of allocated chunks which are allocated from the tree-body allocator. Each chunk has some meta information in the beginning, and the bins on each chunk are used to store the actual data which is returned to the user. The paper shows improvement over the CUDA allocator, but unfortunately it is not publicly available. Lastly, Oroboros is the most recent addition to the field of dynamic memory management in 2020 and builds on array-based queues for memory reuse. It houses a memory manager at the start of its memory region and places its queue at the end. The rest can be allocated as equally sized chunks, leaving the beginning as linearly addressable memory. A queue is fixed size and has a front and a back pointer, and can either directly reference pages returned to the user or chunks with free pages on them. Since these queues have to be potentially quite large, they introduced two variants to virtualize them, to reduce the overhead and only store the currently required part of the queue on the same chunks which are used for the allocations themselves. The first variant uses a smaller chunk pointer array to reference these queue chunks, while the second only requires a front and a back pointer and is represented as a linked list. Allocations larger than the chunk size can either be handled by stacking instances of Oroboros with larger chunk sizes or by relaying to the CUDA allocator. After this introduction, let's now come to the interesting part with the results. All performance data was captured on an Nvidia Titan V. For additional results on an RTX 2080 Ti, which overall follows the same pattern, please take a look at the repository. In this first test case, we evaluated allocation performance for 100,000 allocating threads for all approaches. Here is CUDA in green, with the characteristic staircase pattern aligned to powers of 2, and also the visible reset at around 2 kilobytes, which leads us to believe that multiple larger chunk sizes are used. HALOCK in gold already greatly outperforms CUDA for smaller allocations, and we can also see where it switches to the CUDA allocator at around 3 kilobytes. Chunk-based Oroboros in shades of blue is mainly focused on memory efficiency, but still outperforms CUDA until the first split, while page-based Oroboros in shades of red clearly performs best over the whole tested range. We also include a simple baseline which just atomically increases an offset into memory, here given in brown. Variants of RIFF in shades of violet initially perform better than the CUDA allocator, but also trail off for large allocations, and we can clearly see the performance fluctuations. Scatter-alloc in teal is a performance winner for smaller allocations, and only falls back once it has to switch from hashing to searching its allocation space for large allocations. Malloc is quite unstable at higher thread counts, but if it runs, it falls into the mid-range segment regarding performance. Overall, Scatter-alloc is the clear choice for smaller allocations, with page-based Oroboros the overall best choice. Considering deallocation performance, CUDA once again shows the characteristic staircase pattern and clearly takes the longest amount of time. HALOCK is orders of magnitude faster until it relays to CUDA. Chunk-based Oroboros and page-based Oroboros are a bit slower, as additional to updating state information, items have to be actually inserted into the queues. RIFF only updates states, hence it's consistently fast, while Scatter-alloc shows the split between scattering and searching quite clearly. Malloc is a bit slower overall, but once again does not handle large thread counts very well. Overall, CUDA is clearly slowest, followed with some gap by the rest. One thing to keep in mind are the orders of magnitude difference between allocation and deallocation performance. So when we consider both, allocation performance is clearly the more important factor. Here we can see a snapshot of our test looking at performance scaling, where we tested for all powers of 2 between 16 bytes and 8 kilobytes the performance scaling for 1 to 1 million threads. For 16 bytes, HALOCK is clearly the fastest, followed by HALOCK and page-based Oroboros, and even XMalloc is keeping up. The other approaches show a significantly steeper curve for higher thread counts and are overall slower. For large allocation sizes, page-based Oroboros takes the lead with scatter-alloc and HALOCK slowing down. To evaluate memory fragmentation, we performed 100,000 allocations for the respective sizes and looked at the address range of the returned memory. The optimal baseline is plotted in black here. Interestingly, CUDA always returns the maximum address range, returning pointers at both ends of the manageable memory. HALOCK is quite close to the baseline and the second best approach overall, only jumping to larger ranges once the handoff to CUDA occurs. All variants of Oroboros return virtually the same address ranges, which is due to the queues and their focus on memory efficiency. Variants of RIFF require larger range, especially those variants which utilize one memory offset per multiprocessor. Scatter-alloc also needs a larger range, which is expected due to the scattering of the memory accesses. Only once the searching stage starts, it performs as well as Oroboros. And lastly, XMalloc again is too unstable, but also seems to utilize the full address space at all times. Next, we looked at our performance for out of memory by performing 100,000 allocations for the respective sizes until each system reports out of memory. The plot here shows the ratio compared to the baseline. To reduce the runtime for this test case, instead of instantiating each approach with 8 GB, we just instantiate each one with 2 GB of manageable memory. CUDA is an outlier in this test case, as it was the only one to be always stopped by the 1-hour timeout, but it showed that it slowed down by orders of magnitude over time, from milliseconds for the first rounds to tens of seconds for rounds later on. HALOCK performs better, and here once again the split is quite noticeable between 2 KB and 4 KB, where the handoff to CUDA occurs. All variants of Oroboros perform very similar, with the virtualized variants being slightly more efficient, staying around 98% efficiency after 16 bytes, which is the smallest size that can be allocated from Oroboros. RIFF is mostly held back by unstable execution, mostly failing due to some error instead of actually running out of memory. Scatter-alloc performs second best overall and even matches Oroboros for large allocation sizes. XMalloc once again was mostly stopped by crashes. Overall, Oroboros performs best, followed by scatter-alloc and then CUDA. To test real-world performance, we looked at dynamic graph management, where we tested initialization as well as updating a dynamic graph with different techniques. Here we show update performance on 6 graphs with 100,000 updates focused on a smaller range of vertices, emulating higher update pressure to a few adjacencies. Overall, scatter-alloc, HALOCK and page-based Oroboros perform very well, with some gap to chunk-based Oroboros, which is followed by RIFF and CUDA, is once again clearly the slowest approach. To answer the question posed in the title of our paper, are dynamic memory managers on GPU slow? We wanted to compare the approaches to the canonical approach of storing the memory requirements per thread in an array, performing then an exclusive sum using a library, for example CUP, allocating the whole range and then going back to the device with the corresponding offsets per thread. The baseline you can see here, shown in black, is using CUP. And for this test case, we let each thread randomly choose a size between 4 bytes and 4 kilobytes. The approaches that are clearly slower for reasonable numbers of threads include CUDA, HALOCK, chunk-based Oroboros, all variants of RIFF, as well as XMalloc. These only stay close to the canonical version for very small thread counts and fall significantly behind for 10,000 threads and more. But page-based Oroboros, as well as scatter-alloc, perform much better and even outperform the canonical baseline up to 50,000 threads, with page-based Oroboros even staying close up to millions of threads. This clearly shows that at least some memory managers can compete with the canonical approach, and should present a viable option going forward. Lastly, we also wanted to investigate memory access performance to the returned memory for each approach. The bar plot here shows the slowdown compared to the baseline, which can obviously pack the memory densely for the best memory access pattern. Overall, all variants except CUDA stay reasonably close to the baseline. The best performers include Oroboros, ScatterHallock, HALOCK and XMalloc, with only RegF falling slightly behind as well as CUDA. To now conclude this talk, I want to spend some time detailing advantages as well as disadvantages for the presented approaches, and then end on some guidelines based on the evaluation data gathered during this study. The CUDA allocator, as the oldest but also best maintained allocator, is very reliable and shows consistent performance. But especially for small allocations, it's clearly the slowest with some margin. It seems not to benefit from reuse over time and also slows down once the manageable memory area fills up. XMalloc performs quite well for small allocations, but is clearly held back by its age, as it is quite unstable and frequently crashes for large allocations or mixed allocations. ScatterHallock, despite its age, is still the fastest allocator for small allocations and also shows very consistent performance between thread-based and warp-based allocation. Only large allocations and fragmentation can be drawn up as potential drawbacks. RegF shines when it comes to register footprint and can hold its own with warp-based performance, but is not quite stable and performance can vary quite a bit, and it also slows down over time. HALOCK performs very well for small allocations, and warp performance for small thread counts makes it the second best performer, and fragmentation is also kept in check. The split to CUDA brings with it the expected downsides, and thread performance does not necessarily match warp performance. And page-based Oroboros and chunk-based Oroboros can be viewed separately here. Page-based is overall the fastest, with efficient reuse and great performance, but chunks allocated to a page size remain with this size. Chunk-based is clearly focused on memory efficiency, which it shows but then falls back when we look at performance, only performing middle of the pack there. I'd like to leave you now with some guidelines on when to use which allocator, which are based on the evaluation data gathered. Considering thread-based allocation, for smaller allocations, ScatterHallock is the clear choice, followed by page-based Oroboros and HALOCK. For large allocations, page-based Oroboros is the best choice, followed by ScatterHallock, HALOCK, and CUDA. Considering warp-based performance, the story remains the same, only that the distinction between small and large allocations happens a little bit later, and HALOCK improves its performance. Overall, ScatterHallock for smaller and page-based Oroboros for large allocations still remains the best choice. Oroboros performs best when looking at memory utilization and fragmentation, followed by ScatterHallock and HALOCK. Register footprint is smallest with RegF, as is expected, followed by CUDA and then page-based Oroboros as well as HALOCK. Only ScatterHallock and Oroboros natively support changes to the size of the manageable memory area, and lastly, only Oroboros and CUDA natively built on architectures before and after Volta. The rest has to be compiled with backwards compatibility at the moment and would at least require the updating of the synchronization primitives. If you want to get the full results on all experiments for both cards, as well as the code to integrate the memory managers into your projects, or simply rerun the experiments on different cards, please take a look at our repository. At the end, I hope this talk and paper provide some value and clarity in regards to dynamic memory management on GPUs. And I'd like to thank you all for watching and hopefully talk to some of you at the conference.